All right. Okay. Thanks, Sandip. Thanks again to the organizers for inviting me here. I'll continue with the thread from yesterday. So let me just quickly recap what we discussed yesterday. I introduced the basic idea of a qubit as a two-level system and how that allows you to create new kinds of states, which is superposition and entangled states, and how that can give rise to new possibilities, and which is sort of now well known that having these abilities allows you to do certain calculations, which otherwise will be impossible. We then went on to discuss the generic model of a quantum computer as just a collection of qubits with some interactions, but with some specific requirements on ability to control and measure them. And then I went in a little bit of detail on one particular type of superconducting qubit, how it's measured, and discussed briefly about how you actually implement the so-called quantum gates, which are essentially operations on either single qubits, which correspond to these rotations along the Bloch sphere, and then also multiple qubits where you have to invoke some kind of conditional evolution of one qubit dependent on the state of the other, and how that is important or crucial to be able to create entangled states. Otherwise, it's not really a very useful network of qubits. So we will continue today with some more technical details on how one actually does these experiments. And then I will discuss in the later half of the talk about how certain important developments sort of led to the improvement of these devices. And that sort of also indicates where theory played a role in coming up with those inventions, and then experiments implemented, and how in many cases the experimental requirements also guided the theoretical research. And I'll end the talk by giving some status update of what's been happening in the world in terms of quantum computing results and where we are going next. Okay. So the first slide for today is kind of very engineering type, but it's important to tell you that. I made this case that at the end of the day, all quantum gates is just some microwave frequency pulse. So you need to be able to create with your hardware, your equipment, a generic pulse which has some time varying amplitude and phase, right? So we can write that simply like this, where this omega is at microwave frequencies and there is some amplitude envelope and some phase varying of time. Usually a of t and phi of t are slower functions compared to omega, right? So this is the typical way one writes amplitude and phase modulated. You can break this down into two components by just expanding the sine omega t plus phi, and you write it as two terms, one proportional to sine of omega t and one proportional to cosine of omega t. So now this amplitude and phase dependence sort of gets combined into a single phase dependent, which we now call as I of t, which stands for in phase signal, multiplied by sine omega t plus q of t, which stands for quadrature phase signal, and cos omega t. The reason for writing it like this is that this is sort of how you actually generate these signals in hardware. So what you do is you use a microwave generator. This is like a laser for microwave frequencies, but much cheaper and much more stable to generate this sine of omega t. If you have sine, it's easy to generate the cosine as well with just a phase shifter. And then you use something called an arbitrary waveform generator, which allows you to digitally program what this I of t and q of t are. So as I again said, the time varying, like the rates at which these signals vary is slower than the frequency. So these are envelope functions. And then you need something to carry out this operation, and for that you have something called an RF mixer. It's essentially a multiplier, and this automatically generates the cosine from the sine internally. So you just send in sine of omega t, I of t, and q of t, and then it creates I sine omega t plus q into cosine omega t at the output. And this is how you actually generate these pulses. Of course, there are lots of caveats that this object doesn't exactly produce this, so you have to calibrate it and things like that. And the same object mixer is also used in the reverse. And this is for the measurement part, because you again, for measurement, you're sending a microwave frequency pulse, at some higher frequency, usually around 7 gigahertz or so. And then when you want to recover the information, you typically mix it down to some lower frequency, which is again in these I and Q. So the same object actually works in reverse. If you send in a high frequency signal and a reference signal, it will mix them and give you the low frequency envelopes of the same. So for people who are familiar with the optics notation, this is essentially homodyne and heterodyne detection kind of techniques done at microwave frequencies. And then you can use this. And for many years, this was the approach that was being used. But now with some improvements in signal generation technology, you can actually do it in a lot simpler way and also at a much lower cost, which is using something called direct digital synthesis. Now, of course, if I go back and say, look, I have a very fast digital to analog converter, the arbitrary waveform generators are also digital to analog converter based, right? You program it digitally, but usually they run at lower frequency. And this is because to have a very fast digital to analog converter, something which can generate 6 gigahertz directly, you have to typically sample, if we invoke Nyquist sampling theorem, you have to sample at least twice that frequency, usually much more. So making digital to analog converters which have a sampling frequency of 50 gigasamples per second is actually quite expensive. They do exist and you can buy them. But recently, partly triggered by requirements of 5G mobile technology, a new kind of devices started coming, and it's actually something which was very surprising when I learned about it, because I used to think I knew a lot about digital signal processing. This Nyquist theorem is actually not often specified in its truest form. The way we learn about it is that if you want to digitize a signal of frequency f, you at least have to sample it twice per cycle. That's the Nyquist theorem. And the very hand-waving argument is that, well, you better catch the trough and the crest, at least of the sine wave, and then that sort of gives you some crude representation of the underlying signal. If you don't sample enough, you don't capture the shape of that signal faithfully. That's the typical Nyquist criterion you learn about. But it turns out that that's actually not strictly necessary. The more strict condition, or I don't know whether they call it strict or relaxed, is that your sampling has to be twice the bandwidth of the signal, not necessarily the carrier frequencies signal. And you can think of this from the information content kind of idea, because I could always, so let me take a very specific example, right? FM radio. The signals from the audio, from the radio station are traveling at around 100 megahertz, right? This is the number you dial in your radio station. But the signal it's carrying is audio. That only goes up to 20 kilohertz. So the way we think about it is that this 100 megahertz signal has sidebands in which this audio is encoded. So when you demodulate, you are recovering the audio, okay? But now imagine doing this in a digital domain. When we record audio in digital domain in our CDs or in our MP3 files, we don't digitize it based on the 100 megahertz carrier, we just digitize it based on the 20 kilohertz maximum frequency, which is usually the cutoff for sound, right? So it's the information which is specified by the bandwidth, which specifies how fast you have to digitize. But there are some other caveats. So basically what happens in these things is that these digital to analog converters and analog to digital converters run at a frequency which is lower than the frequencies they are generating or outputting or receiving. And this is purely because of the nonlinearity of the process. And you can do that. So now you have slow DACs, and with some analog signal processing, you can actually create higher frequencies. And this is, again, as I said, partly it was driven by the requirement for your modern 5G phones, which also use very high frequency carriers. And you needed a cheap way to encode your voice and then recover your voice and data, on that.
Here you're saying you just need the EFT and 5FT. Sin omega t comes for free because it's like a 10.
In this case, you actually don't need anything. You just digitally specify the signal at the frequency you want. the system will figure out what is the corresponding digital wave it needs to create so that the correct frequency is created. So you're actually specifying everything. The main point is that even though the signal is at 5 gigahertz, the bandwidth is maybe only 100 megahertz or so, right? That depends on how fast the pulse is changing and things like that. And when that is the case, you can use these techniques.
So the formula you have, the bandwidth has to do with the
how
of
A of t and phi of t.
So you only
Exactly.
want that. And the omega t is coming for free. That's the
Absolutely. The omega t is kind of coming for free. It's also true that omega t cannot be arbitrarily large. It has to be somewhere nearby. Basically, what happens is that the further away omega t is, the more inefficient this process becomes and your signal power will keep dropping. So usually, these systems will run at 1 gigahertz sampling frequency and are able to generate 5 and 6 gigahertz signals and even digitize them very faithfully. So this actually has made a big impact. There's now a lot of open source projects and commercial products which are using this technique to bring the costs down for generating this. And why this is important from the scalability aspect is that ultimately a quantum computer is going to need thousands or millions of channels. Right? Each channel needs a signal to be generated and digitized. So if you don't bring these costs down, the total cost of such systems will become insane. So I'm sure there is going to be many more developments here which will bring the costs even down. So these are actually evaluation boards available from the manufacturer, and you can program them, and we are also using this, and many other groups around the world are also using this technique. Yeah.
Who manufactures these?
This particular board is manufactured by, it's an evaluation board by the company which makes the chip itself, which is Xilinx. So one of the things we will be doing in the future here is to buy the chips and manufacture the boards here. This is something which is going to happen. PCB manufacturing, especially, particularly these high-end ones, because these are very high-frequency boards, so the design and fabrication is non-trivial, but that capacity is now slowly increasing in the country. Okay, so let me now move down to the cryogenic stage. So here on the right-hand side is a picture of a dilution refrigerator. So yesterday I made a point about why you have to be at 10 millikelvin for these superconducting circuits. So this is the inside of a dilution refrigerator, and you can see there are these circular plates. Each of these plates sits at a different temperature and keeps going down as indicated here. And all your main experiments, your qubits and all the associated things, they're all bolted to this plate and it gets cooled together with that. But in order to probe them and control them, you need to bring in the signal from the top. So you can sort of see these little cables here, and there's a block diagram of what's actually going down. And this is actually representing the block diagram for controlling one qubit. Okay. So you need signal lines which bring the signal in, then you have lines which take the signal back out. You have additional lines which actually provide power for another device, which I'll briefly mention, which is actually an amplifier as the first stage amplification for the signals you're detecting. So I just remembered, Spenta, you had asked one question yesterday about the temperature of other quantum computing systems as well. So I just wanted to use this picture to point out that the cooling for us, I like to call it as bulk cooling, right? You're cooling massive pieces of material down to 10 millikelvin. If you compare this to an ion trap system, how do you define the temperature there? It's temperature of what? It's not the temperature of the equipment or any piece of metal which is at cold temperatures, but it's the temperature as inferred by the energy of those ions which are no longer moving, right? They're confined with basically using laser cooling techniques. So those temperatures actually are even lower than 10 millikelvin, right? So a stationary atom would be at absolute zero. Of course, we can't do that. So there, the cooling is for a very small number of objects, like the atoms or the ions you are trying to trap. Whereas here, it's bulk. So the requirements are different, the technology is different. It is difficult to compare one versus the other. But you will often hear the ion trappers say that we don't need cooling systems. But their lasers are doing exactly that, except that they are cooling hundreds of atoms. Here we are cooling billions of atoms together. So it's just a very different way of thinking about it. Okay, so why all of this stuff? There are lots of technical challenges of making a device operate at 10 millikelvin. Now, first of all, most of your signal generation and detection instruments have to sit at room temperature, though there is a separate line of research to make cryogenic versions of those as well. But still, at the end of the day, the signal has to come out of the refrigerator, right? Which means you have to put some wires in and out of the fridge, but you are taking it all the way down to 10 millikelvin. You have to do it in a way that you don't bring in additional heat or additional noise into your device while attempting to do this. And this is non-trivial. So I cannot run a copper wire all the way down because copper will just thermally short all of my temperature stages and my fridge won't cool down. So you have to use thermally insulating somewhat, so it's a price you pay because of Wiedemann-Franz law. If it's a metal, if you have poor thermal conductivity, you also have poor electrical conductivity. So you try to balance that out, and you use things like stainless steel, alloys like copper, nickel, beryllium, copper to make these coaxial cables so that they don't bring in too much heat and the 10 millikelvin stage remains close to 10 millikelvin. And at the same time, they are not attenuating your electrical signal so much that you have to put in enormous amounts of power at room temperature. Now, it turns out that such cables exist and the numbers are actually quite reasonable. In fact, from the attenuation perspective, we intentionally put more attenuation on the lines as shown by these yellow boxes here. This is not for thermal reasons, but it is for noise reasons. When you have any generator of a signal at room temperature, it will have Johnson noise corresponding to that temperature, right? And usually these transmission lines have something called a characteristic impedance of about 50 ohms. So you can think that at the very least, the noise emanated by a 50 ohm resistor at room temperature is going to come out of that generator along with the signal, the sinusoidal signal you're trying to generate, right? And you say, well, why is that a problem? Well, because I want my oscillator sitting at 10 millikelvin to indeed be in its quantum ground state. If I put in 300 Kelvin radiation down the line, it's just going to completely overwhelm the device. So you put attenuators to kill that noise, and you have to distribute them at different temperatures. So the way you think about it, so 20 decibels is a factor of 100 in power, and power and temperature have sort of the same correspondence. So it's a factor of 100 in temperature in terms of the noise of that signal. So 300 Kelvin radiation is coming down and it hits this 20 dB attenuator and it becomes 3 Kelvin radiation, okay, at the output. It gets knocked down by a factor of 100, but the fact that this resistor is sitting at 4 Kelvin, it will also radiate Johnson noise, or you can call it black body radiation if you want, at 4 Kelvin. So approximately the output noise here will be 7 Kelvin. So 4 Kelvin from the fact that it is sitting at 4 Kelvin, and 3 Kelvin, which is the knockdown version of the 300 Kelvin radiation. So then you typically put one more here to knock that down by another factor of 100 and another at the lowest temperature. So that by the time you reach 10 millikelvin stage, all the noise from the higher temperature has become completely insignificant. And the price you pay for it is that your control signals now have to be boosted by that same factor, but that's okay because the amount of power you need at the level of the device is already very small because these, the energy scales of these devices is small. So typical instruments which can generate signals at the level of millivolts or volts is absolutely fine, despite putting all of this attenuation in the line. Now, when you are going out, then you have to be a little bit more careful. I cannot put attenuators because I'll be killing my signal. So what you do is, for the first stage, you use now a superconducting coaxial cable. Now, superconductors break the Wiedemann-Franz law. They are perfect conductors of electricity and extremely poor conductors of heat. So it's actually perfect, but of course, you can only operate at low enough temperatures. The typical alloy which is used is niobium titanium, which has a transition temperature of around 8 or 10 Kelvin. So up to the 4 Kelvin stage, you run a superconducting coaxial cable all the way up, and then you put an amplifier there. You can buy commercial, what are called high electron mobility bait transistors amplifiers, which can sit at 4 Kelvin and work. They're typically made using 3,5 semiconductors like indium phosphide. And then you have boosted the signal enough that you don't care about subsequent losses due to a regular coaxial line, because after 4 Kelvin up to room temperature, we don't have superconducting coaxial cables. Right? So we then use regular stainless or copper nickel kind of wires. So this amplifier becomes critical, but typically we actually have an amplifier at the 10 millikelvin stage. These amplifiers are specialized amplifiers which use the Josephson junction's nonlinearity to give you the gain. So a lot of research and a good part of my PhD in postdoctoral work was on actually development of this particular device. And these are some of the world's quietest amplifiers. What do I mean by that? It turns out that when you amplify a signal, nature says that you cannot do it without adding noise. And the minimum amount of noise is stipulated by quantum mechanics. And it's purely an argument which is based on, if you do the statistics of the signal at the input and the output, and if you want the commutation relations to obey, you see that some extra noise has to be added. But quantum mechanics sets the minimum amount of noise you have to add. Most amplifiers which we use in daily life are far from that limit. They're like orders of magnitude worse. These devices go very, very close or operate at the quantum limit of amplifiers. And this is again critical because the signals we are using to probe the devices is so small. And remember yesterday I showed you these histograms which were overlapping. If you want those histograms to be as narrow as possible, you have to minimize the noise to the smallest possible limit set by nature. So these components help you achieve that. And then there's a bunch of other filters. You also have to introduce, so here are the list. So you have coaxial cables, you have attenuators to kill the thermal noise, you have reflective filters to kill out-of-band noise so that they don't reach your device. You also have something called infrared blocking filters, which turn out that these cables can actually allow these terahertz radiation, blackbody radiation from 4 Kelvin come down quite easily, and the energy is big enough to break Cooper pairs in your superconductors. So not only you have to shield your devices, you also have to put in specific devices. The one which is marked here as silver lossy, this by the way is some internal lab notation, so it has made it just looks silvery, so it's called silver lossy filter. These help you block signals at 50 and 100 gigahertz and above. Now those signals have no meaning in terms of operation of the device, but they can break Cooper pairs. So you have to design them specifically to put in there. So if you just look at the count of components here, there's already something like 15 to 20 pieces here for just 1 qubit control. This is one of the biggest challenges in terms of, but it's not a fundamental challenge, it's a technical, logistical challenge. That if you're talking about thousands of qubits, this becomes a mess. And I think just yesterday we were talking that every time somebody sees a picture of a quantum computer, it just looks like lots of wires are coming out of it. And that's the reason. I mean, this is a nearly empty fridge. But when you put all of this stuff, the whole thing gets really, really packed. And finally, one has to worry about the size of this refrigerator and the cooling capacity of this refrigerator. Because as you bring in thousands of these lines, even though you have worked hard to ensure the heat load is small, it adds up. So you have to build massive dilution refrigerators to be able to account for future larger systems. And if some of you have been following, IBM is working with one of the refrigerator manufacturers to build gigantic refrigerators like the size of the room, and they're modular. You can actually put multiple of them together to create an effectively larger system. But currently, most of the sort of commercially available dilution refrigerators can handle, I would say, quantum computers up to about 1,000 qubits without you having to make these very highly specialized kind of systems. Yeah. So then you also have these things which are shown in red here. These things allow microwave signals to go in a particular direction. So that's all required to ensure that your signal path is exactly as you want it to be. So it depends on the type of the fridge, but typically that number varies from 24 to 48 hours. But it's fully automated. So what you do is you prepare your experiment, you do everything, then you close it up. So closing up here means you have to put radiation shields on all of these plates, and then you have a vacuum can, you close that up, and then you just push a button. And then you can go home and come back after a day and it'll be cool. So the automation software takes care of cooling. A bulk of the time which actually is needed to cool the system is actually to go from about 300 Kelvin to about 4 Kelvin. These, maybe I can go into a little bit of detail. There are two refrigerators in this system. One which you can see here with this little tube. This allows you to get down to these two temperatures, 55 Kelvin and 4 Kelvin. And once you have reached that temperature, then this other system which is on the back side, you can see these little tubes here, that is called the dilution unit. That then kicks in and takes you further from 4 Kelvin down to 10 millikelvin. But as you add mass to an empty fridge may cool down in 24 hours, but as you add all of these things, it adds thermal mass to the base temperature plate, and that slows down. So it can take 2 days. But there are some options where you can flow liquid nitrogen through it to make it faster. So it really depends, but the average time I would say is about 1 to 2 days, depending on the system. That depends on the experiment. If you have a working quantum computer, you'll cool it down and you'll just keep it there. And these systems can run for like 6 months, a year without any problem. Yeah. Yes? Mm-hmm. I wouldn't say easy versus difficult, it's different, right? I'm a low temperature physicist, I know how to operate this. For trapped ions, you need lasers, essentially. All the cooling is done by shining lasers at appropriate locations and then doing the protocols right so that the ions slow down. So if you know how to use lasers, for you that is easy, if you know how to use this. But I don't know, that's why it's difficult to compare even the costs for them, because it's like very different kind of an equipment. But you don't need cryogenic systems like this, it's optical cooling, so yeah. Though in some cases they have, I think, tried cooling some parts of the system down to lower temperatures for low noise operation for other reasons, because like if the traps themselves are cold, then they can actually give you better performance. But I might be saying something wrong here, but I remember reading about it somewhere. Yeah, so this is just to give you a sense of the complexity of these experiments. Yes? The what? Which component blocks it? Well, so it's not, I mean, by microwave background, you're not talking about CMB, right? Yeah, so not 4 Kelvin from outer space, but the fact that this plate is at 4 Kelvin, and this plate is going to radiate black body radiation corresponding to 4 Kelvin. And there is enough of a tail in the flux of photons that is generated that if I don't shield my device, those photons will actually hit the superconductor and break Cooper pairs and give rise to dissipation. So for free space black body radiation, we use radiation shields. So essentially it's just a metallic box, a Faraday cage if you like, which is cooled at this temperature. And it's perfectly light tight. And your chip resides inside that so that this photon doesn't come in. But the same photons, because this cable is going through those temperature stages, that can actually send in high frequency radiation. So you might ask me, why doesn't this 20 dB work for that? Because these are not designed to work at infrared frequencies. They're only designed to work at microwave frequencies where we are using them. So these are frequencies which we actually, this came as a surprise, you know, when the device qualities improved, suddenly we see that, and Spenta yesterday we had asked about this, this is one of the reasons for the non-equilibrium population. like suddenly we started seeing that the qubits were not at 10 millikelvin, but the apparent temperature looked like 50 or 100 millikelvin. And then people realized that it's because of this. And then you just make, it's basically like you make a filter which is designed to let everything through in the frequency of interest. And then it's like basically like black powder. It just blocks all higher frequencies. So those are inline. So you have to worry about radiation coming through your transmission lines, which are not designed to work at those frequencies, and radiation just bouncing around the free space around it. We don't have to worry about outer space. That's the whole thing is inside. But we do have to worry about, and people have done some experiments, that cosmic rays every once in a while go through your device. I mean, nothing is stopping them. And people have looked at that. People have also studied by having radiation sources nearby to see how they affect the devices. The verdict is still a little confusing. Some people got really worried in between and was, okay, do we need to like put lead lining around our devices now? But then there were some estimates which said that it's not going to be such a big problem, but we do see it. And I remember during my PhD days, my advisor talking about that, and we all thought that, okay, he's just like, lost it. Because these devices would actually suddenly randomly misbehave for no apparent reason. And such events do happen. And in fact, this has been even documented in regular computer chips. But the possibility of that is, I think, very, very small. I forget, there was a YouTube documentary about this, but it's a famous event where I don't know whether a lottery or something got messed up, and an event happened which is like some 1 in a billion kind of a possibility. And it was ultimately attributed that maybe a cosmic ray went through a transistor and flipped a 0 to 1. So I will look this up and send it to you. I'm not making this up. So yeah, so there are cosmic influences of that type which can affect your experiments as well. Yes, that's what we thought. It's like, all right, we can always just blame them, right? So I'll now go through a few standard steps we do to characterize these devices. So the first thing is always spectroscopy. You want to know where the qubit is in the frequency space, right? Even though we design them to have a particular inductance and a particular capacitance, we can never hit them absolutely precisely, though it's getting better and better. But we know that it will be roughly around 5 gigahertz. And then basically what you do is, you do a two-tone experiment. You send a fixed frequency tone at the measurement frequency. So this thing is monitoring the cavity. Remember, the cavity's frequency shifts when the qubit state changes. So that is actually the monitoring signal. And then you use a probe signal, which is sweeping the frequency, and you then monitor the phase of that. And you get curves like this. So this is an example from a device which actually has 3 qubits in the same one, and the frequency axis is broken because they're at different frequencies. And you see these little dips in your phase curve when the probe tone becomes resonant with one of the qubits. Okay, so just pay attention to these ones which are marked right now, these fatter ones. These are actually the identified omega 01 transition for qubit A, B, and C. But what is this other line, right? This other line is actually because of the fact that these qubits are not two-level systems. And because these states are almost harmonic oscillator-like states, only nearest neighbor transitions are allowed. And a transition from 0 directly to 2 cannot be done in a single order process. So you have to have a 2-photon process. And these lines are actually corresponding to half the frequency difference between 0 and 2. So this is actually 0, 2 by 2. So using these 2 frequencies, we actually now know the first 3 levels of this system. So this is important because we have to make sure that the nonlinearity intended for this device is as designed. So these are the 2 things we always look for. And this is sharper because you have to actually send in, this is a weak process to excite. So it's not coupled so strongly to the environment as well. And usually in order to be able to see these other lines, you have to excite the system at higher powers, which power broadens the main line, which is why these things look much fatter. if the actual qubit lines were this fat, they will hardly have any coherence, right? Because this line width is a measure of dissipation as well. But this is how you start by probing it, and because you're also continuously measuring it, that also gives a line width to this thing. So this is how you identify approximately where your qubit frequency is, and then you can start your manipulations, right? So the next thing you do is the Rabi oscillation experiment, which I already mentioned yesterday, where you send in a pulse at that resonant frequency you have identified, and you vary the time of that pulse, and then you follow it by measurement. You repeat it many, many times for accumulating statistics, and you do it for different pulse widths, and you get this kind of a sinusoidal oscillation, where the qubit is going from the ground state to the excited state, back to the ground state. And it's decaying because this coherent oscillation is disturbed by decoherence events, so the phases get randomized as you make the pulses longer and longer, and it sort of, you can see that it's going and settling up at about 0.5. That would correspond to a perfectly mixed state. Now, in order to actually do use these in quantum computing type experiments, you have to fine-tune this.
What is this PFE?
Probability of being in the excited state. Okay. This is, you can also just think of this is sort of normalized. Otherwise, you can also just think of this as phase shift, where this value will correspond to the phase of the microwave for the ground state, and that value will correspond to the phase of the excited state. And because we know that it's bounded by these two values, we can normalize that result. Okay. So what we actually do is we zoom in to this first part of the curve, and then you basically say that, okay, if I had made a pulse of this length, then this is a pulse which is going to take my ground state to the excited state. This is called a pi pulse, because on the Bloch sphere, it's a rotation of pi. So it will do the same rotation irrespective of where you started. So if you started in the excited state, you'll go to the ground state. If you started in some superposition state, you'll go to the opposite side on the Bloch sphere, and so on and so forth. Right? So this is again the first identification, and the point which is exactly halfway is called a pi/2 pulse, and that's the pulse you can use to create an equal superposition of ground and excited state. Right? Now this again is sort of the second step in identification. Usually after this, we very fine-tune, both the amplitude and the time to be very precisely, because remember, this is a continuous analog quantity. It's not frozen at 1 or 0. So if your pulse is slightly off, your rotation will be slightly more or less. So you have to really fine-tune this. So there are various follow-up experiments which you do to fine-tune these pulses so that you know that you're as close to a pi pulse or as close to a pi/2 pulse. Otherwise, your algorithm after a few steps will be all over the place. Okay, so these are parts, and there are other experiments to characterize how good these pulses are. Typically, they consist of putting the same pulse over and over again, and as you do that, you accumulate errors, and you can see how the system deviates from the predicted state it needs to be in. Okay. So this is how you do the calibration. Then you typically look at characterizing your coherence times of your system. The simplest one is to look at the relaxation time, and that's very easy. You have figured out how to do the pi pulse, which takes you to the excited state. You then, so you apply that pulse, you wait for some time, and then you measure. And then you plot the same quantity, the probability of being in the excited state, as a function of this wait time. So for 0 wait time, of course, you started at the excited state, so everything is in 1. But as you delay this, the state slowly decays back to 0 in an exponential form. Right? All of these are ensemble measurements. They're repeated many, many times to give you this statistical average. This is the measurement of your relaxation time. So you fit an exponential to this, and the time constant is what is called as T1, or the relaxation time of this system. Right? So this is just measuring this process. I showed you this data here. This is an ensemble measurement of the decay event, and these are individual events of the decay, which I showed you yesterday, like where the excited state is decaying back to the ground state in this jump-like fashion, but with a very large time distribution. So if you actually collect enough of these and average them, you will recover that curve. By the way, the sense is opposite here. The excited state is on the top here. Here, the excited state is in the bottom. That's just, how we did the experiment.
Those lines which are connecting the two going up, say, are they extrapolations or are they actual measurements?
No, they are actual measurements. So there is a response time of your detector, right? The qubit itself probably is transitioning much, much faster than that. but your detector has a finite bandwidth. So this line width of that thing is a reflection of that.
Wasn't the yesterday, what are the different colored lines?
They are just 6 different identical experiments. So the experiment is you start the system in the excited state and immediately start measuring, and you monitor the phase continuously rather than having a finite pulse and taking the time delay. You just imagine that this sine wave was started right here and it kept going. And then you look at the phase of that sine wave as a function of time along the signal, and that's what is plotted here. And when the qubit changes state, the phase shifts, and that corresponds to this change here. And so this is basically like a radioactive atom emitting a photon at some random events. This is exactly that.
So the time, the fact that the times are different is just random.
Yes, this is your Poisson distribution of this process. But
It's always 1 to 0, it's never 0 to 1.
well, we created the system mostly in in 1. Because of that, it's 1 to 0. But if I waited long enough here, you will see occasional jumps back to 1. And this again is a reflection of the fact that the system is not in the quantum ground state. There is always some thermal excitation which is left. And that's actually how we infer this effective temperature. We look at how many transitions are going up versus down. So that was the relaxation process. We then move on to looking at the dephasing process. So, and remember that dephasing I had mentioned as typically being due to slow fluctuations in the energy levels of the qubit itself, and that gives rise to errors in the phase of a superposition. And the way you do that experiment is slightly more complicated, but let me just walk you through it. So you put a pi/2 pulse, which now brings you to the equator. So that's an equal superposition. Then you wait for some time, and then you put another pi/2 pulse. Okay, and then you measure. And what this does is that it allows the qubit to evolve freely between these two pi/2 pulses. So if the frequency is very stable, then you have very deterministic output after these two pi/2 pulses. And that's essentially an oscillation which would go from 0 to 1 back to 0. But because during this time the frequency is fluctuating, you accumulate phase errors, and that also causes these oscillations to decay slowly. So this decay constant is due to that aspect and also due to the fact that the qubits can decay to the ground state. And you get a decay constant time T2, which is related to this pure dephasing T5 and then 1/2 of the T1 as well. So from the previous T1 measurement and this measurement, we can get the dephasing time.
Frequency is fluctuating. This is the
Omega 01.
And why does it fluctuate?
Could be many things. So in these kind of devices, it could be due to charge noise. It could be some movement in the dielectric of the capacitor, which gives rise to small fluctuations in the dielectric constant. So there are many ways. It can also be due to unwanted photons in the measurement cavity. If you have some thermal population in the measurement cavity, that will give rise to a stark shift effect in a random way that can shift the frequencies. So these processes always are present, and in fact, these are the causes for the decoherence, which you have to minimize as much as possible. So these are the typical two numbers you will see, when somebody is characterizing a qubit's quality, a T1 time and a T2 time. There are more sophisticated versions of this experiment where you can put a pi pulse right in the middle, and this is called the echo sequence. So for those who are maybe familiar with the NMR echo sequence, it's basically a version of that. And that kills the lowest frequency noise of the problem. And the reason is that, so you're talking about noise which is constant during this period, but it's changing from one iteration to another. So by putting a pi pulse, you actually invert the evolution, so it cancels itself out. So it would deviate in one direction and then it will deviate back to the same way because the noise is constant during that window. And that also allows you to get a sense for what kind of improvement you can do by adding these kind of echo pulses, which are more generically known as dynamic decoupling pulses as well. So these introduce an overhead, but you can protect your device from very slow noise in your system, which you can correct by these kind of cancellation techniques. Okay. So then at the end of the day, if you look at what
Sorry.
happens in a quantum
Sorry, I have
algorithm.
a question.
Yeah. Sorry.
There was the T1, which was this relaxation, and T2 was the dephasing, but what was this T5 that you have?
This is the pure dephasing. So this experiment gives you this decay time is called T2, but it's composed of two parts. The thing is, even if this process was not happening, this experiment will always give you a decaying sine wave. Because of the fact that, so think about it like this. If delta t was infinite, you will always find the system in the ground state before you apply this pulse, which means the measurement will always give you 0.5 at long time intervals. So that means the oscillations have died down, right? And at some point, at smaller times, the oscillations will be finite. So even if this process, which is what we are actually trying to characterize, did not exist, this experiment will always give you a decaying sine wave whose coefficient will be 1 over 2t1. But this process now makes this decay faster, and that's how you break it down into this thing. So this comes from very simple noise analysis of a two-level system with the right kind of noise flavors and all, like a lot of text which derive this formula. So but we need to know the two different components. Because you've already measured your T1, you can then say, okay, then this kind of a process is controlled by this number. And this process also has a spectrum in the sense that how is the frequency varying? Is it varying very quickly? Is it varying very slowly? And the slow parts can be cancelled out by this by putting a pi pulse in the middle, because it essentially cancels the evolution. The noise is constant during one iteration, so you let the noise allow you to drift in one direction, but because of the pi pulse, in the second half it actually comes back. These echo sequences are very common in NMR, and they used to know about your environment. So yeah, so basically I was saying that at the end of the day, so this is a sort of a simple quantum circuit of how these algorithms are represented. You have different qubits along different lines here, and then this is the time axis, and these boxes tell you what operation is being carried out on that. So a collection of these operations involving 1 qubit or 2 qubits or 3 qubits is what's called as a quantum circuit or a quantum algorithm. Each of these operations or boxes in the experiment is implemented with some microwave pulse. Okay? So at the end of the day, you're just bombarding your processor with a bunch of microwave pulses, and then finally you send a final bombardment of measurement pulses. You look at what comes out, and that gives you the result. Right? So experimentally, that is what is going on. So that's sort of what's there, and the exact microwave pulse to perform this operation has to be calibrated very precisely. Those calibrations can drift over time because the qubit property can drift, your electronics can drift, so you have to keep checking it over and over again and make sure that the pulses are now still doing the same operation you are trying to do. Because you would like to be ultimately limited not by errors in your electronics, but by the fundamental errors due to decoherence, right? Or other problems like coherent errors. So you have to make sure that you reach that limit, and so you have to keep doing that. And ultimately, as I mentioned yesterday, the coherence time tells you how many such gates you can put before the final answer loses all meaning. Right? If you keep sending lots of pulses, you can be sure that the answer is completely random and will have no meaning at all. So currently that is the case, but if you have error correction, then you can do much longer. Yeah, so the simple things which can drift is your electronics, right? It's like I asked it to create a pulse whose amplitude was 1 volt. But after some point of time, which could be due to changes in the temperature of the room or some noise in the electronics, it might produce 1.01 volts. That will change what the pulse will do to the qubit. It will no longer be a pi pulse, it might be pi into 1% pulse. So that is an error now, because you are expecting it to do something, it's doing something slightly different. So you have to recheck this and then adjust the amplitude so that you will now say, okay, generate 0.99, but it will actually generate 1 now. Okay, so that's the simple technical aspect. But the qubits themselves actually change over time. So one of the things which happens is that the energy level separation, which you have to know very precisely, can fluctuate or even drift it might be 5.1234 gigahertz today, but after an hour, it could have changed in the last 2 digits or so. And these things happen due to all kinds of reasons. It could be due to some trapped magnetic vortex, shifting a little bit. It could be some defect in the dielectric constant, in the dielectric of the substrate. Something has drifted into a different configuration, and that has changed the electromagnetic field distribution and hence the capacitance or the inductance of the device. So this all sounds really scary, I'm sure, for a theorist, but these are realities of doing experiment, right? So that's why I think back in the day, solid state physics used to be called squalid state physics or something like that, right? So, but these are there, but at some very small level. And sometimes due to cosmic rays and other events, it could just completely get changed. And often, and this is true for small academic labs or to the state-of-the-art labs in IBM and Google, that often when we see these changes, so what we do is we warm the system up and then we cool it back down. And the system reconfigures and goes back to being okay. Or it goes back to being something completely different. So these are all tricks we use, and sometimes we also send some very large power to knock things, to shake things up, to sort of move the system back into the regime. Now, ideally, going forward, as these systems become more and more complicated, and you want to really use them, not just have fun with them, then these kind of processes should come down. And there, you have to worry about materials engineering, what is the quality of your substrate, how clean are all the surfaces, so that these random defects. So a very simple way of thinking about this, if everything was perfectly crystalline, right, then everything is ordered, everything is in this sort of some robust low energy state. But if things are not so great at the boundaries, a bond could break and move into a different direction. And it could happen due to quantum mechanical tunneling as well. Now, there are metastable states these bonds could take, or the configurations could take. And if this happens inside the Josephson junction tunnel barrier, which is like 1 nanometer thick, then it will change the transparency of that barrier. That directly translates to the change in an inductance of the barrier. And that directly translates to a change in the frequency of the qubit. So these are the fluctuations, and if they are small, all we have to do is just recalibrate everything to that new values and everything goes back to being okay. But you have to keep monitoring it. Okay. All right. So we will now move on to these different qubits. So one very nice thing about this field is you actually have 3 building blocks. You have a capacitor, you have your usual inductor, and you have the Josephson junction, which gives you the nonlinear inductance. And by combining these 3 objects in different ways, essentially you are creating your own designer Hamiltonian. When you write down the quantum mechanical Hamiltonian and draw some potential well and look at the quanta's energy levels, it is entirely controlled by these 3 things. So it's like you have a Lego kit at your disposal, and only your imagination sort of restricts you from making interesting circuits. So what it's interesting for, of course, depends on the application, but over the years, these are some examples of various kinds of qubits which have been invented, and they are plotted on this sort of these axes which are related to the ratios of the Josephson inductance to the linear inductance, and some energy associated with the capacitance and the Josephson inductance. That's just a convenient way of plotting it. And this is in this review article, this is now almost more than 10 years old. This is sort of called as the periodic table of the artificial atoms. So superconducting qubits were also given the nickname of artificial atoms, because you can have an anharmonic energy level structure like an atom, but you are designing them. So you can have a single well, you can have a double well, you can have asymmetric potentials. This is all entirely up to you. And then in addition to this, you can have magnetic flux flowing through these loops. That also acts like a control parameter.
This is for a single qubit.
You can, yeah, see.
What if I wanted a multi-qubit Hamiltonian, like I wanted to alter things, then is that?
Yeah, so there are 2 ways of thinking about multi-qubit Hamiltonians, and there's one example later on. Multiple qubit systems are typically just collections of these objects with some interaction between them.
But can I
Right?
do in that interaction
Of course, yeah. So when we look at 2-qubit physics, you have to take that interaction into account and write the Hamiltonian of the combined system. The measurement architecture also uses two objects. It uses a nonlinear oscillator, which is the qubit, and a linear oscillator, which is the measurement cavity. In order to know how that works, you have to write down the Jaynes-Cumming Hamiltonian of two interacting oscillators. And then you take the approximation and the right limit to do that. But yes, you can do it for any number of, you can even do it for some infinite chain of these things and write down the Hamiltonian for that as well. Yeah. Yeah. Yeah.
I want to ask a small follow-up.
Yeah.
Let's say I wanted a gauge theory in these qubits, for instance, which has some long-range interaction between one qubit and another. Like, is that also something we can do? Not that it's very interesting for the main thing you're talking about.
I mean, see, theoretically, if you can imagine the circuit, you can solve it, assuming it's solvable. Experimentally, having long-range interactions is hard, because you have to have some physical connection between them. There are some ways where you can extend the interaction long range, and some of our research at TIFR has been trying to look at, but by long range there, we don't necessarily mean very, very long range, but at least it's not nearest neighbor, right? So that's definitely possible. It's a practical difficulty of how you create those connections. In other systems like atomic systems and trapped ion systems, you can do some of those things a little bit more easily, either through a common mode. So all these individual qubits, they share a common mode. So if you interact with that mode, it doesn't matter where you are in that chain, because it's a common mode across the entire chain. In neutral atoms, there is a technique where you excite one of the atoms to a Rydberg state, where the dipole becomes huge. And if you do that for two different atoms, and they could be far away, they can now start interacting because they are both in these highly excited states. That is another way of creating long-range interaction. But in the circuit picture, it's a little bit harder to get very long-range kind of systems. Yeah.
Before moving on, so I didn't quite, what's on the y-axis here?
It's actually exactly this.
I see, okay.
So
some ratio of capacitance.
Yeah, so it's basically capacitance over Josephson inductance and Josephson inductance over linear inductance.
And so, for example, I hear the word fluxonium and so on. It's just this device, but operating at some other radio band.
So the position here tells you what are the ratios which are being used here. So if you actually look at this line here, this all corresponds to this axis being 0, right? Which means so Lj cannot be 0 because Lj is the Josephson inductance. It means L is infinite, okay? And L being infinite is because it is a parallel circuit. I don't know enough, you have to remember you're an engineer. So, when you say I don't have an inductance, that is equivalent to saying the infinite inductance is infinite here because it's in parallel, so you can just remove it. So all these qubits don't have a linear inductor. They only have a Josephson junction and a capacitor. Then all of these other qubits have inductances of varying value. So that's really what it means. So you will see the specific circuits in the next few slides here. So all of these emerged, first initially from curiosity of analyzing some circuits, but then from trying to get this Hamiltonian to have particular properties. So the rest of the talk is, apart from the last bit, is going to be looking at a few of these examples and to understand why they behave the way they do, right?
So you will of course elaborate, but
Yeah.
there are advantages in terms of coherence time.
Absolutely. Yes, that's one of the reasons they have evolved. But if you are using these systems for doing some general physics type of experiments, then you don't worry about those kind of things necessarily, right? Now, one of the first qubits which was invented, it was called the charge qubit or the Cooper pair box. And it kind of looks like this. And this intersection here between two Josephson junctions and the capacitor is often called the island. Okay? Because this is an isolated piece of superconductor which is not directly connected to any metallic reservoir, but it's interrupted by a Josephson junction on two sides and a capacitor on the third side. And I want to distinguish this from the simple qubit I explained earlier, which is just an oscillator, right? And it was very easy to say, okay, yes, oscillator, quantized states, two lower states, I can understand how quantum mechanics enter the picture. But back in the day, for some reason, I don't know, they were not thinking about oscillators. I don't know why, but I mean, I also grew up on these devices first. The idea of quantization was really thought in terms of, okay, I should be able to count some quantity one at a time, right? What is that quantity here? It's the charge on this island. Because it's this isolated island which has, where if you now put a charge here, and now because this is all superconductors, we now talk about Cooper pairs. If you have a Cooper pair here, it sort of gets trapped because it has a tunneling barrier on either side and a capacitive barrier on the other side. And there is a finite energy cost to add Cooper pairs to this island. So this is how the idea of quantization and quantum stuff entering electrical circuits used to be taught in that day, is that you can now see that the number of charge on this island could be quantized, and that could become a degree of freedom, right? It's of course not a perfectly isolated system, because if you do that, then you cannot really manipulate it. But the role of the Josephson junction and the capacitance enters in terms of energy scales in the problem. There's a Josephson energy scale, and then there is a charging energy scale, which determines how the charge on this island would behave and whether charge is a good quantum number at all. And it's a continuous space. Depending on the parameters, you can have charge to be a good quantum number, or your eigenstates could be superpositions of many different charge states. Right? So you can define these quantities. So charging energy is a Cooper pair square. So it's essentially E square over 2C. So charge square divided by the total capacitance. So this capacitance is basically the capacitance of the two Josephson junctions and this so-called gate capacitor. And you can also apply a voltage to sort of affect the potential of this island. That also affects how charges can move across this. And then you have the Josephson energy, which is basically related to the critical current of these junctions, and it's related to this flux h bar over 2 pi here. And then you write down the Hamiltonian in the charge basis, where this represents the charge on this particular island. So you have a charge which is just directly related to the number of charges times the charging energy with this offset from this voltage. And then you have this hopping term, which allows for the charges to change, but that costs an energy because it has to tunnel through the Josephson barrier. So when you now solve this Hamiltonian and you look at the eigen energies, you can get in some generic case where the charging energy is not very big compared to the Josephson energy. And you can now plot these eigenstates here as a function of this voltage or effective gate charge on this island. And you see that this ground state and the excited states are actually quite varying depending on this particular voltage. This was a problem because if you have any noise on this, then the energy level separation between these two is not fixed. So in these earlier qubits, you had to apply a bias, and typically you went to a point where there was an extrema in these two energy levels. So here, the first order derivative with respect to this variable is 0. And that's where you will get the best coherence time for this particular device. And the dashed lines here are, you see, they are like parabolic curves. So this is just the first term of the Hamiltonian with the Josephson term set to 0. So what the Josephson term does, it opens up a gap in this spectrum. So you can kind of think of this, instead of these two degenerate energy levels, they split up by a value which is in the small Ej over Ec limit exactly equal to Ej or 2Ej. So this was the first qubit, and at these operating points, charge was not really a good quantum number. It's not really, you cannot say that this is exactly 0 excess charge and 1 excess charge, but it is mostly there. And the smaller Ej over Ec ratio is, and the closer you are to this kind of limit, the charge becomes a good quantum number. But at this degenerate point, it's anyway, at the very least, symmetric and antisymmetric combinations of 0 and 1 excess Cooper pair on that island. So in these early experiments, there was a lot of decoherence because it turned out that even if your voltage source did not have noise in it, the substrates you had, there was always jiggling charges around it. So some random charge fluctuation always used to couple to this island and give rise to fluctuations in this axis, even if you did not do anything to it. And that limited the decoherence times of this. This was called charge noise. It was so bad, people tried many things, but it's like something which is always present. So one had to move away from this kind of a picture to get more coherent qubits. Moreover, if you operated here, there was, because these two states correspond to symmetric and antisymmetric combinations of 0 and 1 charge, there was no difference in the charge between those two states, because the expectation value of both 0 plus 1 and 0 minus 1 in terms of the average charge is the same. So how do I detect which state the qubit is in? Because the standard detection techniques used to be using some another device which is sensitive to the charge on this island, and that would, so these were like these radio frequency single electron transistors kind of techniques. So what you did was that when you were doing manipulations, you sat here, and then when you were ready to measure, you moved away from this point to give some difference in charge between the two states, and then that could be detected. So that caused more problems, because then you would have some decoherence as soon as you moved away, but because you're ready to measure, it was not such a big problem, but on the whole, these kind of devices didn't do very well. Now, to solve this measurement problem, a small variation in the circuit was done, which was this so-called charge phase qubit, okay? Just pay attention to this part of the circuit. You see, it looks exactly the same. You have your island. The thing is sort of mirror image, the capacitors on this side, and you have your two junctions here. But now, instead of this just being a loop, there is a big junction which is inserted into this loop. And that junction is centered with this capacitor. This essentially introduced an orthogonal axis through which you could probe the system. So now you not only had charge, but you also had a phase difference across these junctions. And that allowed you to measure an orthogonal quantity which depended now on the state of the qubit without moving away from that charge insensitive point. Okay. So this was actually a big improvement in the coherence times, where these dephasing times went from few nanoseconds to about 200 nanoseconds. And for the first time, you could see these very clean Ramsey fringe experiment, which I showed you with those two pi by 2 pulses. This was 2002, and this experiment was done at Suckley using this experiment. So just as a side personal note, this was around the time I started my PhD career. So my life started looking at this paper first. And one of the scientists here moved from Suckley to Yale, and he was my PhD advisor. And my project was to figure out how to do this measurement, but using microwave techniques instead of using these low frequency techniques, where you actually passed a large current and that generated quasi-particles. So you had to wait a long time for them to settle down. So my PhD thesis was on how to use this qubit circuit, which is good in terms of dephasing time, because it can always stay at the at the sweet spot, and then use microwave techniques to measure this. So
Where is the tuning part in the diagram on the right?
These voltages and all, so they all come from these lines here, out here. What you're seeing in the middle is just like this part of the circuit. So all of these voltages and all will connect to these little metallic electrodes here. This one, for example, that's the gate electrode. And then they go out onto the circuit board, onto the wires from the rest of the fridge. So the highlights were, you can operate at the so-called sweet spot. You are insensitive to charge noise to first order. But because there is no charge signal, you measure along the phase axis where you get a signal, and then you can get this very nice Ramsey oscillations. And I think Norman Ramsey gave an autograph on one of these printouts to my advisor at that time to confirm that, yes, these are indeed Ramsey fringes. Because this was the first time they had been done in this kind of a device of a single qubit, right? And of course, there were many further works, including many in which I was involved at Yale. So this is what I did for my PhD thesis. We used this oscillator to do the measurement using RF techniques. Okay. So this actually finally led to the development of the transmon qubit, which is what I explained most of last class, right? And this was happening right next doors. in the neighboring lab. In fact, we shared lab space. And the point I made about how the thought process of thinking about quantized states was so different that it took us, like people in my lab, quite a bit of time to, at least the students, to understand why this even works, because we were not even thinking in terms of oscillators and quantized states of oscillators, right? And this basically, all it does, the circuit is actually the same. It's still junctions and a capacitor, but the Josephson and capacitive energy ratio is different. And this sequence of diagrams sort of tells you what happens to these eigenstates as you go from a ratio where the Josephson energy to charging energy is small to something which is very large. So you are making the charging energy contribution become smaller and smaller. So initially, as a function of this gate voltage, you have large variations in these eigenstates. And as you slowly increase this ratio, they flatten out, and now you have like a harmonic oscillator kind of ladder, which no longer depends on this axis. And if it no longer depends on this axis, any noise on this axis has no consequence on the energy level separation, right? But it was very strange to us because we said, well, how can this work if there is no charge, nothing is changing, how can you measure? It turns out that if you couple the right device to it, you can measure some other quantity, which is what eventually happened. And the main trick here, which came out of the theory group of Steve Gervin at Yale and led by Jens Koch, was to understand this fact that as you went along this axis, you pay a price, which is that this energy spectrum is highly anharmonic, right? If I was operating here, I could call this a very good two-level system because the third level is so far away. But out here, the third level is very close by. In fact, it's closer to 1 than 1 is to 0. It has what is called as negative anharmonicity. But, and the advantage you are getting is how flat these bands were getting, right? So this is essentially a thing of saying, what is the charge dispersion as you go from 1 electron to 0 electron? How much is the frequency changing? What they found was that the charge dispersion, which is basically connected to how sensitive you are to noise, was decreasing exponentially, whereas the price you were paying was sort of only polynomial. So you did not, so the worry was you will end up with a harmonic oscillator by the time it became useful for you in terms of charge noise, but it did not happen. And that came from understanding the physics of this system, and that's what these two plots show, is that you have exponential suppression of the charge sensitivity or charge dispersion, whereas only polynomial effect on how the nonlinearity of the system is there. And there's a sweet spot around EJ over EC ratio of around between 50 to 100. So all transmon qubits operate in this regime. Okay. So you trade anharmonicity for exponentially reduced charge dispersion, and there is sufficient anharmonicity for fast operation. What I mean by that is that because you now have nearby levels, you cannot send very short pulses to go from ground to the excited state and vice versa, because those very short pulses have broad frequency content and they can excite you from 1 to 2. So you are now going outside the subspace of the qubit, which is also bad. It's called a leakage error. But it was big enough, typically that number is about 2 to 300 megahertz, the difference between 0, 1 and 1 to 2, whereas the 0, 1 transition itself will be around 5 gigahertz. So it was good enough that you could do fast gates, but there is still a case to be made for making a qubit more nonlinear so that you can go even faster. Because again, you're fighting decoherence, faster is better, right? And the quantum state measurement was still possible by applying, by basically dispersively coupling this to a cavity and using the dispersive limit of the Jaynes-Cummings Hamiltonian. So this very seminal paper sort of laid down all of these theoretical analysis that you have low charge noise sensitivity, you have decent anharmonicity, and you can make a measurement with good signal to noise ratio. So that sort of ushered in the era of transmon and good times, coherence times. So a few years later, this other type of qubit was invented, and this actually also came not from wanting to improve the anharmonicity or wanting to improve coherence times. They actually were trying to invent an experiment where you could count charges one at a time so that you can create a current standard, right, from a fundamental basis. So they were looking at various versions of these circuits, and they accidentally came to a device which turned out to be a good qubit. Now, look at the circuit of this qubit here. It's a Josephson junction shunted with a capacitor. So far looks exactly like a transmon, but now there is a large linear inductor which is shunted in parallel. Okay. Now, in practice, this linear inductor is actually not created by a piece of wire. It's created with an array of Josephson junctions. Now, there are some practical, technical reasons for that. I can explain if somebody is interested. But for now, you just have a large inductor here. This also turns out to be insensitive to charge noise, without having to go to an EGO or EC ratio here, which will make it very linear. A very naive hand-waving way of thinking about it is that this inductor is like a short circuit for low frequency charges, right? You cannot keep a charge difference across these two terminals because it is connected by a short circuit. So that's one way of thinking, is that charge difference cannot accumulate across that other device. This is a very hand-waving electrical engineering kind of expose. Of course, the right thing to do is you solve the Hamiltonian and you see how the eigenstates look like. Now, what should the potential of this thing look like? Remember that Josephson junction has a cosine potential, and the inductance has a parabolic potential. And the values are such that you can imagine this as a parabola which is modulated by a cosine. Okay, so this is how it looks like. So this is sort of the lowest part of that parabola, and when there is zero flux in this loop, because now there is a loop here, a superconducting loop, the flux here becomes important. So if you have zero flux loop, you see that at the bottom of the well, so this is like the parabola coming here like this, and then there are these undulations due to the Josephson junction, right? And then you have these quantized levels. There is one here, then there are these two sort of nearly degenerate levels, and so on and so forth. And if you now apply a finite amount of flux, this whole thing gets tilted like this. So you have a very rich energy level structure, but for the qubit operation, you actually go to half a flux quantum, where the energy levels look like this. At the bottom, you have this very small double well potential. So you cannot think of this as your underlying parabola, and this small double well potential gives rise to two nearly degenerate states, which are split by the tunnel splitting between these two barriers, right? And because of this very weak splitting, first of all, the energy difference between these two is much smaller. Usually the fluxonium qubit, and these are your qubit levels, by the way. These frequencies, instead of being in 5 gigahertz, they are usually around a few hundred megahertz. Some people have even measured down to 10 megahertz or so. That give rise to other kind of challenges. But because of this very weak tunnel splitting, so it's like, it's like almost two localized states on either side of the barrier. It's almost classical, right? So the coupling between them is very weak. So that basically means the matrix element of these two levels is very, very small. So the environment cannot cause it to decay very quickly. You have to drive it harder to do operations, but it's very nicely protected. So this is one example of how engineering the Hamiltonian and engineering the matrix elements allows you to protect against noise, right? But the same device is still measurable using the same technique where you have a linear oscillator, and this linear oscillator is still at a much higher frequency, and then you wonder like, okay, these frequency differences are so big, how can this qubit have any effect on this oscillator? It turns out it's because of this level. The cavity couples to this transition, which is close to the cavity, and when the qubit goes from the ground to the excited state, it actually pushes on those levels and gives rise to a finite shift in the cavity frequency. So despite the qubit and the cavity frequencies being very different, unlike a transmon where they're typically close to each other, this device is still measurable, and the role is played by these higher levels, right? They don't participate in the qubit dynamics, but they play a role in the measurement dynamics. So again, this is a very nice and beautiful example of how with simple changes in this circuit, you can get very different types of behavior in the Hamiltonian, and there is really a lot more possible. Okay, so right, so I have 5 minutes on that clock, so I'll try to wrap up quickly now. Okay, so now a lot of experiments are being done using this particular qubit, and it could emerge as a potential replacement for the transmon going forward. Even though transmon is also marching ahead in terms of the coherence times, the main advantage is the fact that it's a highly anharmonic system, so it's a lot more closer to a two-level system. You don't have to worry about leakage errors so much, which means you can do much faster operations. But these are still in early days where people have shown now 2-qubit gates with these experiments, but a larger kind of processor is not yet built. And about a year back, we also started making these kind of devices in our lab. So as one last example, I wanted to show a multi-qubit device. So coming back to what you were asking. So in this is one of the first experiments we did in our lab now almost maybe 7-8 years ago, and it was a subject of the thesis of my first student, where we were reimagining the building blocks of this. So you now see a more complicated circuit, but really it's 4 junctions in this kind of a square array, and then you can imagine a capacitance between each of these nodes. In reality, the device just looks like this. There are these 4 junctions, which are actually in the form of squid loops for other reasons, and there are these 4 pads, and there's capacitance between each pad to every other pad, and that's it. And if you look at this circuit, and the parameters are all in this transmon regime, so they are like oscillator, weakly nonlinear oscillators. What we showed is that this circuit has 3 normal modes of oscillation. So it's not that this is 1 qubit and this is 1 qubit. This whole thing is a 3-qubit system where you analyze this and you get 3 normal modes, each at different frequency, and each normal mode is actually an anharmonic oscillator ladder. So it behaves like 3 different qubits, but because it's part of the same circuit, the nonlinear terms give rise to always having interactions. So a more accurate way of thinking about this, rather than 3 individual qubits, is that if we take the 2 lowest levels of each of these subspace, it's an 8-level Hilbert space. And there were some advantages that certain 3-qubit gates here became very, very easy. So in fact, it looks like this. The lowest lying energy level structures of the computation subspace looks like this. You have 8 levels, and they are all connected by these transitions, which are all first-order transitions. So by driving at these frequencies, I have universal control over this 8-level system or a 3-qubit system. So we then showed that this makes, in fact, it's kind of funny here, the 3-qubit gates are the simplest gates to do. And the single qubit gates are the most difficult gates to do in this architecture, because you cannot really think of them as individual qubits. So it gives rise to a single pulse generalized 3-qubit gate, and we showed that if you run this Grover's search algorithm with these 3 qubits, because of the advantages of this structure, it was actually a lot more efficient than running it on the conventional system where every qubit was separate. So there are other works here where we are trying to build in blocks of these units of 3 while retaining the advantages of this kind of a system. Okay, so the last thing about this, I wanted to come back to this measurement problem. So, this is your qubit coupled to your cavity. If you now correspond this to the cavity QED experiments, you have atom inside a Fabry-Perot cavity. It's the same physics, except that here it's not a 2-level atom, but you can approximate it like that. So this is described by the Jaynes-Cumming Hamiltonian. So here's your spin half 2-level system, here's your harmonic oscillator, and here is the exchange coupling term, essentially saying that I create a photon in the cavity, kill 1 photon in the atom, and vice versa. Right? Now, this, of course, typically describes the resonant process where the frequency of the qubit and the cavity are the same. But if you go to the dispersive regime where these are detuned and they are far off resonance compared to the coupling strength, you get a simplified version of this Hamiltonian, which looks like the qubit plus a modified cavity, which depends now on the state of the qubit. So omega r plus chi sigma z means the resonant frequency of the cavity is dependent on the value of sigma z. That's the principle behind the measurement which I explained yesterday, right? And this gives rise to resonant curves, and you can do the measurement. But as I showed you yesterday, when we do these measurements, instead of getting two nicely separated distributions, you get these little bumps on the other side. Like the excited state goes to the ground state and the ground state goes to the excited state. The simple explanation here, of course, there is decoherence, so the system is relaxing, but it turns out that when I try to probe this cavity by adding photons, that itself causes these changes to happen. Now, if you go back and stare at this Hamiltonian, that process should not be allowed because it's not energy conserving, because the cavity photons are at a very different frequency compared to the qubit photons. But this is not the actual Hamiltonian, right? The underlying Hamiltonian was this previous one. So people analyze this in detail and they see that there are non-RWA terms one has to worry about, and that can give rise to some resonances in this subspace, which can cause the qubits to go between 0 and 1. And not only that, because transmon is a multi-level qubit, you can actually even escape the computational subsets while you're doing this measurement. Now, why is this important? See, because the size of the signal is purely dependent on the noise and the magnitude of the signal. So I could have chosen to put a lot more photons and gotten a much bigger signal out of this. But when I try to do that, these processes take over and give me more and more errors. I'm trying to separate the histograms so that they have small overlap error, but I'm starting to introduce these mixing errors due to the qubits actually changing state. If I could solve that problem, that is minimize that mixing, then I can make a much better readout. And you would really like these errors to become 1 part in 10 to the 4, 10 to the 5 in order to be useful in quantum computing systems for the future. So one of the attempts we are doing is that we change the circuit slightly. So instead of two coupled harmonic oscillators or one harmonic, we sort of introduced a coupling. This actually is very similar to the contronium circuit, which is why we call this the contramon. And what essentially happens is that if you analyze this Hamiltonian, let me go back to the previous slide, you actually get this same Hamiltonian directly without doing any approximations from the original Hamiltonian. Okay. Because this interaction term comes directly from the symmetry of this circuit. And this was, by the way, not the intention when we started, but what we saw is that in this device, we were able to put a lot more power. See, this measurement was done using this low noise amplifier and we got something like 98% fidelity, whereas this experiment was done on this device without the low noise amplifier and we still got 97% fidelity. And this was possible because I was just able to put in a lot more photons before these bad things started to happen. So this has been now ongoing for several years. We are sort of approaching some kind of a conclusion, but this has entirely got to do with the nature of the Hamiltonian and what happens at these high excitation levels. And this is still an open problem. We probably need to improve these circuits even more to really understand how to suppress these kind of errors to get better measurement results. So that was basically it. Just in the last couple of minutes, I will run through some big results, which I'm sure many of you have seen. Back in 2019, Google did this big announcement with 53 qubits that there was the first computation which was significantly faster than the best classical version. They claimed 200 seconds on their quantum computer versus 10,000 years estimate on the most powerful supercomputer. A lot of people objected to this, but this was again on a problem which is not really of practical interest. It was really sort of constructed to be something which a quantum computer can do quite easily. A couple of years later,
They might have been a later problem, but could they do it reliably given no error correction and so on?
Yeah. So this doesn't require error correction for this. This is you're just looking at the output of a randomized circuit. And you say that what it will take a classical computer to do that. And the reason is that because it's a very big 53 qubit system.
So I think there's no error correction, because whatever is the output
is the output, exactly.
If it's with errors, it's with errors.
Yeah.
Is that the point?
Yes.
So it wasn't a real computation.
No. But you see, you have to start somewhere, right? You come up with a problem, you say, here's the quantum computer, it is producing this result. What would it take to a blessed classical computer to do that? And that's the advantages. Of course, that's why this was also controversial. Some years later, a Chinese group performed the experiment with slightly larger number of qubits. They had a more modest difference of 1.2 hours on the quantum versus 8 years on the classical. But it's exactly the same kind of a problem. But still these are big numbers. I think after some point of time, it doesn't matter whether it's 10 years or 10,000 years. So, and somebody likened this to be like, this is going to be like your Bell's inequality experiments, right? There's not going to be a definitive endpoint. These kind of comparisons will keep going on as computers become better, and you show more and more sort of better comparisons with that. A big challenge is that once the number of qubits becomes large enough, it often becomes impossible to have an equivalent classical estimate because there is no way to do that. And you then come up with best estimates. So last year, IBM came up with another angle saying that there is some evidence of usefulness in quantum computing before fault tolerance, that before error correction can be introduced. They did that in their 127 qubit systems with fairly decent coherence times. And essentially, it was again a demonstration where it showed that some computation of expectation values of a certain problem can be done much more efficiently than a classical computer, using some other techniques where they can actually understand the noise in the system. I had mentioned this yesterday, called error mitigation as well. So that's basically it. To summarize, maybe I'll just say that this platform is highly coherent and highly flexible for doing experiments in the quantum regime. The ability to different types of Hamiltonians, which I hope I conveyed, allows it for not only applications in quantum computing, but a lot of things which I have not mentioned. People have done very interesting quantum physics experiments and quantum optics experiments in regimes previously not possible, especially the ultra-strong coupling regimes are there, and there's a whole line of research in that. It is also the most advanced and most promising platform for building a proper computer. But there are still some where I think the basic block is reasonably well understood, but it can be improved. The qubit can be made better. Maybe there's a different design just waiting to be discovered. And again, that's where theory can play a role with, guided by experimental inputs. But to make any large-scale system, you need resources, you need good quality fabrication, electronics, engineering, and you need time to do that. And these are sort of the basic things. You have to make your blocks more robust. You have to improve the electronics to be cheaper and scalable. The idea of having slightly longer range connectivity can also help in making this efficient, and then ultimately, being able to do quantum error correction and reaching the fault tolerant regime of quantum computing. So, thank you. I'll take any questions.
Thanks a lot, Vijay. Any questions, comments? Maybe I can ask you one. It's open-ended, so you can answer over tea later.
Sure.
But I mean, it's fascinating to see how you can engineer each qubit to specifications. And of course, here perhaps you were looking at quantum computing or getting qubits and so on, but just also from the point of view of sensing or building detectors. So one hears about obvious transition edge detectors and so on, but could you use these for interesting detection experiments?
Right. So, see, any quantum two-level system can be turned into a sensor if you could make it sensitive to a particular quantity of interest. Now, if you specifically talk about superconducting platform, the applications of such sensors are very limited because of the cryogenic requirement, right? If you want a very sensitive magnetic field sensor, you want to take it out in the field. So there are other platforms like Diamond and things like that, which are a lot more promising for that. When I was doing my postdoc in the neighboring lab, they were actually trying to use squid-based systems for doing MRI. So, even though the squid was still at the cryogenic temperatures, but it was a very specially designed probe where a pickup coil could be at room temperature and still be coupling some signals onto the squid. So it's possible, but it's more complicated. So unless there's a very specific need which can only be met. But on the other hand, as you know, these low noise parametric amplifiers are being used for dark matter search experiments like axion experiments, because there it's particularly those experiments where you have these big cavities, which when it's impinged by your axion particle, it creates a shift in the frequency, and then but that cavity can then be coupled to some cryogenic systems, and these kind of amplifiers can. In fact, these experiments have already happened, and they have set some bound on some of these things. I don't understand the details of the dark matter picture. So of course, there it is there. And then you mentioned transition edge sensor. That is just a superconductivity, using superconductivity as a mechanism for detecting photons, where you bias a wire of superconductor very close to its superconducting transition, so that an incoming photon then triggers it and puts it in the normal state, and that creates a signal which you can detect. It's in a very different regime. You also don't need 10 millikelvin temperatures for some of those experiments. But I think fundamentally as sensors, they will find limited use because of the fact that these devices have to be in the cryogenic environment. But if some mechanism where signals can be coupled into the cryogenic environment, then yes. But there are probably always going to be better alternatives to do that in a simpler fashion. There's one over there. Yeah. There's something called a Sholkoff law of quantum computing, which Professor Robert Sholkoff himself coined as a joke. Not really. I mean, if you look at IBM's roadmap, they have some scaling, but the fabrication techniques are not at the same level and stage like it was for semiconductor industry at that time when people started noticing these trends, right? And as people often find out, Moore's law is more of an economic law rather than a physics or an engineering law. So I think here the progress will be more in spurts and bumps, like there'll be a breakthrough and then suddenly you realize that you can make 1 million qubits a lot more reliably, as opposed to just doing fine-tuning a well-oiled machine to just get more and more improvements in that. Right? It's still happening, right? The transistor sizes haven't been shrunk too much in the recent past, but many years ago, people thought, oh, how can they make it smaller? Because these use optical light, and you have this wavelength-based limit, and you're already there. But then, engineers figured out clever techniques to beat the wavelength limit, and they're still progressing over there. We are in a much different regime when it comes to fabricating these devices, right? If I make 2 identical superconducting chips, let's say with 100 qubits, with the same design, they're not going to be the same. If that was the case for your CPUs, there will be no economy around it, right? So it's a very different scenario. The fabrication is a lot more complicated. There are lots of unknowns, yet the fact that the material controls and things like that make such a big role, it will be a while before some equivalent of a Moore's law will come here. But at the same time, in some sense it's simpler, because with every additional bit or qubit, naively speaking, your computational power doubles because your Hilbert size doubles. Whereas every additional bit in a classical computer is just one additional bit in a classical computer. So it's going to look very different here. Okay, thank you. Thanks.